if people would be willing to turn on their video, because otherwise it's a bit like teaching to a brick wall. But if no one's willing, I guess I'll just have to teach to a brick wall. Anyway, so let's get started. This week, I want to cover something that I think you're going to cover tomorrow. But to me, like, one of the most confusing things in all of Calc 3 is the right-hand rule. And so everyone has their own right-hand rule. Physicists, when they're computing curl, will do a right-hand rule where they have their thumb pointing along the direction of the current flow, and they'll have their fingers curl in the direction of the magnetic force. And I think mathematicians have their own versions of the right-hand rule. And to me, it all gets very complicated because no one can agree what the one and true right-hand rule is. And so I'm just going to tell you what to me is the most straightforward right-hand rule. Okay, so I'm going to draw a beautiful picture, which it's not like Mona Lisa level hands, but it's pretty close. So when the right-hand rule to me is, say this thing is your index finger, and this thing is your middle finger, and then you have two more fingers here. And then your thumb is like this, okay? Wow, amazing. Sometimes I even surprise myself. So what is the right-hand rule used for? Most often it's used for, if you have two vectors, then you want to take a cross product, okay? And when you take a cross product, what it means is you have a couple vectors and you want to find a vector that's perpendicular to the other two, okay? So in 3 space, this is what it looks like. So this is the space spanned by these two vectors, meaning if you know linear algebra, like the space that they generate if you take all sums of them. And then here is a vector perpendicular to these two vectors, okay? And so the problem is when you use the cross product, when you compute the cross product, there are two potential vectors that could come out of this, right? It could either be this one, which points up, or it could be, let me use a different color, this one, which points down, okay? And so the right-hand rule allows you to determine which of these is the correct vector, or which one you're getting out of the cross product. And again, there's nothing inherent about this. Like, there's nothing, yeah, it's not like an intrinsic property of the universe or anything. This is the right-hand rule. It's actually just arbitrary. Like, we define the direction up to be the result of the right-hand rule. And there's nothing else to say about that, okay? We could just as easily define it to be down, but since right-handed people controlled the world for millennia, it just so happens that the right-hand rule gives you the correct vector that comes out of the cross product, okay? So let me show you how it works. Say that you're taking the cross product of two vectors A and B, okay? So you take your index finger and you point your index finger in the direction of A, you point your middle finger in the direction of B, and your thumb points in the direction of the orthogonal vector that you get out, okay? And so, yeah, I guess there's not really anything else to say about this, but let me give you a couple examples of how you compute cross products. Okay, so the first one, why don't we take the vectors 3, 2, 1, and 4, 3, 2, okay? The way that you compute the cross product, it's very similar to taking a determinant, if you've seen this before. So you take I, j, and k. These are the component vectors, the unit component vectors, which are very commonly used if you're a physicist. And then what you do is you just take a determinant. Oh, someone said, I just saw a comment that's actually very good. So that refers to my drawing, which I agree, it's a great drawing. Maybe we should look at it again. Ooh, nice drawing. Okay, so you take the determinant, and how do we do that? You do I hat times 2 times 2 minus 3 times 1. And then we do minus j hat, because remember it's an alternating sum up here. So minus j hat times 3 times 2 minus 4 times 1. And here, remember, we're just taking minors. So like this thing is just the determinant of this minor, which means like a submatrix. And then the determinant that I'm taking and multiplying by j is just the determinant of these two vectors, okay? And then we also have to take the determinant of our last minor, and our last minor is here. And this gives you, so plus k hat times 3 times 3 minus 4 times 2. And so that gives you 4 minus 3 I hat. Okay, I'm just going to do it out because I don't want to write this another time. So 4 minus 3, that gives you 1. So 1 times I hat minus 6 minus 4, that's 2 j hat, plus 9 minus 8, that's k hat, okay? And so there's one other thing that I guess is important to note about the cross product, which is when you're taking the cross product, so you have these two vectors, and what you get out from taking this cross product, the magnitude of the third vector is equal to the parallelogram that's spanned by these two vectors down in the plane, okay? So let's check that what we got out actually worked. So as an exercise right now, I want you to check that I did this calculation correctly. Namely, take this thing and check that it's orthogonal to these two vectors. And what does that mean? Remember, orthogonality in more than 2 dimensions, you can't really talk about right triangles anymore. So all you got to do is take a dot product with the 2 original vectors and make sure what we did worked. Okay, so give me an F in the chat when you're done. Okay, I guess I'm a little short on Fs. So is something confusing to the vast majority of people, or are you just still working? Okay, I have 4 Fs, so I'm happy about that. But what happened to the other, I guess 2 of these participants are me, so 9 people. Are other people confused or? Oh, okay, so 8 people left. 7, great. Okay, so that's satisfactory for me. I'll go over it. So our vector is 1, minus 2, 1. So let's dot this with 3, 2, 1. 3, 2, 1. And this gives us 3 times 1 minus 2 times 2 plus 1 times 1. And so that's 4 minus 4 equals 0. So now we know that it's orthogonal to the first vector. And for the second vector, we take 1 minus 2, 1, and we dot it with 4, 3, 2. And that gives us 4 minus 6 plus 2, which is, of course, equal to 0. And so that means that, indeed, the cross product works. Namely, we put in 2 vectors, we get out something that is orthogonal to them. All right, great. So let's move to the worksheet now. Okay, so why don't you open up the Math 32A Week 2 discussion, and let me get an F in the chat when you have it open. Thanks. All right, so we actually have a lot of important material to cover in this worksheet today. The main topics are parameterizations and Euclidean, or sorry, Cartesian equations, okay? And these are sort of like 2 sides of the same coin. Parameterizations and Cartesian equations are both used in order to cut out surfaces in 3 space. That is, a parameterization is usually it's 1-dimensional. So you take some sort of variable t, and you take t to some sort of object that lives in 3-dimensional space or 4-dimensional space or 13-dimensional space. And so let me give you a couple of examples. The one that I like the most is the spiral. So the spiral is clearly 1-dimensional, and we want to figure out how we can take some variable t and write the spiral in terms of t, okay? And so the way that we would do that is, first, let's think about what this looks like in the x and y coordinates. So we draw a plane, and then imagine wiggling this plane up and down, okay? Then what would happen if we redraw this plane? So basically zoom out or zoom in, is as we move up and down, it's going to cut out a circle in this plane, right? So hopefully people believe me there. If you move this up and down and essentially throw the curve onto this plane, you get a circle. And so as we move up and down, we cut out the circle, and so we can write down an equation for a circle in terms of t, which is cosine t sine t, okay? And so our third coordinate has to represent the fact that as we move this plane up and down, we get this circle, okay? And so as we move forward in time, we move up along the spiral. And so this third coordinate is just going to be a t, okay? So we get cosine t, sine t, and t. And the t represents the fact that we're moving up. The cosine t and sine t gives us that we're moving in a circle in the plane. And there are a few important things to note about this. First, the speed. So if we change t, like say that we put a 2t instead of a t, then this really doesn't change the parameterization at all. Because what we're doing is we're just cutting out the same spiral, but we're doing it more quickly, okay? And so it doesn't matter. All we care about is the final spiral. And so if you were to take a derivative, which you'll learn how to do soon with respect to t, then you would get a different result if you put in a 2t or a t. But if you were to just look at what it cuts out, there's going to be no difference. Someone asked me, is the spiral infinite? And the answer is yes. In this case, the spiral is infinite. But if you wanted to make it into a finite spiral, it would be pretty easy. All you'd have to do is set a range for t to remain in. So you could say like, t runs from 0 to 100, and then you just get a spiral of height 100, okay? And the second thing that I want to cover is Cartesian equations. So these are actually a very popular topic in higher level math, like algebraic geometry. And a Cartesian equation is basically an equation that gives you some sort of surface by its zero set. So let me give you an example. In 2 dimensions, you could have, say, the circle, x squared plus y squared is equal to 4. So that's a circle of radius 2, all right? And so why is this a circle of radius 2? Because all of the pairs x, y satisfying this equation lie on the circle. There's a one-to-one correspondence between pairs satisfying the equation and things on the circle. And so that gives you that these two sets are equal, okay? And so in higher dimensional space, we're going to do the same sort of thing, right? And so let's do a couple of examples. So open up your Math 32A Week 2 discussion, and let's do the second and third problems under problem 1. So problem 1, parts 2 and 3. And give me an F in the chat when you reach some sort of solution. Okay, so I have a couple of Fs. Anyone else? Okay, so I have 6 Fs in the chat. That's not bad. Great. It's more than half. So let me go over it. I think this is good. All right, so first let's find the Cartesian equation for the sphere centered at 5, 2, 0, and passing through 2, 2, minus 2. So the first thing we have to do is figure out how big the sphere is, okay? We have a point at the center, and we know, so it's not the center of the axes, sorry, bad drawing. So we have, say that the center is, it's kind of hard to draw, but maybe it's somewhere up here. And 2, 2, minus 2 is somewhere down here. And so this allows us to ascertain the size of the radius. Let's figure it out by finding the vector that moves between these two vectors, that goes between these two. 5 minus 2, 2 minus 2, and 0 minus 2, right? Because we just subtract them. And that gives us 3, 0, 2. And now we have to find the magnitude of this vector, which is 3 squared plus 2 squared root, and that's equal to the root 13. And now we can write down, what does it mean to be a sphere? It means that the distance from some central point is fixed, and we take all of the points that are this distance from the central point. And the distance of some random point, x, y, z, from the center point, 5, 2, 0, is just x minus 5 squared plus y minus 2 squared plus z minus 0 squared. And then we take the square root. And that's equal to root 13. And so all we have to do is square both sides, and then we end up with this equation, which looks like our familiar equation for a sphere. All right? Hopefully everyone's happy with that. Do I have any questions? No one? Oh, so that's a good question. How did I determine to subtract 2, 2 minus 2 from 5, 2, 0? So it would have been just as good to subtract 5, 2, 0 from 2, 2, 2, 2, 2 minus 2, right? Because all I needed here was the magnitude. And it's just the same to take the magnitude of this vector versus the vector that goes in the opposite direction. Okay, so that's a great question. Any other questions? Okay, let's talk about the second part then. For the second part, how am I doing? Yeah, I'm good on time. We want to find the equation of the infinite height cylinder centered around the y-axis with radius 2. Let me draw that. So here's my y-axis. Actually, I guess it's more common to draw it like this, where you have x, y, and z. X, y, and z. And something interesting here is, if you look at these axes, if you have your index finger pointing towards x, your middle finger pointing towards y, then your thumb points upwards in the direction of z. All right, and so it shows you that the axes actually follow the right-hand rule, where the z-axis is the cross product of the x and y axes. So let's draw the cylinder. The cylinder around the y-axis is going to look like this. And it's just going to stretch on forever. All right? And so it has radius 2. And what does it mean to have radius 2? It means that if we project into the planes spanned by x and z, so x and z, we get a circle of radius 2. And that gives us x squared plus z squared is equal to 2. But now we have to ask about the dependency on y. Y is allowed to be anything, and it doesn't affect the values of x and z. That means that we can just leave y out of our equation and write our equation in terms of x and z. Isn't y usually the diagonal line? I actually don't think so. I think generally when you draw in 3 dimensions, you draw it like this to make sure that it satisfies the right hand. Oh wait, actually, I think you might be right. Yeah, I actually drew it wrong. My apologies. So you should have X, Y, and Z. And then let's see. So X, it depends which way is your positive and negative axes. So if this is positive, then I agree, because then you would still have your index finger pointing towards X, your second finger pointing towards Y, it's a Y, and your thumb pointing up, right? So you just want to make sure that it satisfies the right hand rule. That's really the only requirement. But you're right, I actually drew it wrong there. So thanks. All right. Let's talk about the next problem, problem 2. Let's do problem 2, part 1. And F's in the chat when you're done. I don't have a whole lot of F's. Are people confused? Great. Okay. someone says they don't fully understand the concept of parameterization. That's fine, we'll go over it. And also it's a confusing concept, so you'll get it in time. Let's go over it. We're trying to find a parameterized equation of the line in R3, which contains the points -1, 5, 3, and 2, 4, 6. All right, the way that we're going to go about this is we're going to start with one of these points, and nothing is going to be drawn to scale because it takes too much brain power to do that on the spot. But we're going to start with the point -1, 5, 3, and then we need to find the vector that goes from -1, 5, 3 to 2, 4, 6. And the way that we do that is we take 2, 4, 6 and subtract off -1, 5, 3. This gives us 3, -1, 3. All right, now we can take the point -1, 5, 3, and we can add to it 3, -1, 3 times t. The logic being that if we start at -1, 5, 3, and then we start traveling as time goes above 0 in the direction towards 2, 4, 6, so 2, 4, 6, then we're going to reach 2, 4, 6, and because a line is determined by any 2 points uniquely, if we have some line that passes between these 2 points, we know that we have the unique line, okay? And then we're done. And of course, there are many different parameterizations that you could give for this. For instance, you could change this t to a 100t, okay? And that would just change the speed. You could change it to a -t. You could even, you could rescale this vector however you like. And you could also, instead of starting from -1, 5, 3, you could start from 2, 4, 6 and move in the reverse direction or even in the same direction. It actually doesn't matter as long as you have some line that contains both points. All right? A parameterization is describing a vector as an equation. It's not necessarily a vector, okay? It could be anything, like the spiral. The spiral is not a vector. It's any time that you're taking something in some number of variables and you're writing a surface in terms of it, okay? Since t is just a scalar, it doesn't change the direction, just the speed. Is that the concept here? So it actually does change the direction. If we start at -1, 5, 3, and we put a -t, then before we were moving from -1, 5, 3 towards 2, 4, 6 as time increased. But this time we're just moving in the reverse direction if we change t. But it doesn't matter because it's still a line that contains these two. You just have to take -t and move backwards in order to get back to 2, 4, 6, okay? Does that make sense? Great. Okay. I think you can do problem 2.2 in the privacy of your own home. Let's do problem 2.3 and then call it quits for today. So give me an F in the chat when you've given that a shot. This one's a little bit trickier than the last few. Oh, great. I have one F. All right, I think in the interests of time, I'm going to start going over it because I don't want to run out. And I think it'll take me about 3 minutes to do this. So what we do is we have these two lines and we want to figure out where they intersect, right? So 5 minus 2 minus 1 plus s, 3 minus 1, 2, and 4 minus 7, 11, plus t times 1 minus 2, 5. All we have to do here is set them equal. We get 5 minus 2 minus 1 plus s times 3 minus 1, 2 is equal to 4 minus 7, 11 plus t, 1 minus 2, 5. Now we have to solve this equation, all right? And this gives us, so first let's subtract this from both sides. That gives us 5 minus 4, which is 1, minus 2 minus 7, which is 5, and minus 1 minus 11, which is minus 12. And now let's subtract this term from both sides. That gives us t minus 3s and minus 2t plus 5s and 5t minus 2s, all right? And now all we have to do is solve these equations. These are actually three separate equations. They're t minus 3s is equal to 1, minus 2t plus 5s is equal to 5, and 5t minus 2s is equal to minus 12. And we have to make sure that these have a solution. So the first equation gives us t is equal to 3s plus 1. If we plug that into the second equation, we get minus 2 times 3s plus 1 plus 5s is equal to 5. And that gives us minus 6s minus 2 plus 5s is equal to 5. And so if we condense these terms, we get minus s is equal to 7. And so s is equal to minus 7, okay? Hopefully this is what other people got as well. And then let's solve for t now. So we have t minus 3 times minus 7 is equal to 1. And so that gives us t plus 21 equals 1. And we should get t is equal to 20, minus 20. All right, sorry about the writing, it's getting a little cramped here. And now we just have to check that this satisfies our last equation. And I guess I'm actually a little bit doubtful. Uh-oh, I think I made a mistake. Oops, that does not satisfy our third equation. Does anyone see the mistake? aren't I subtracting S? So S, let's see. So isn't it S minus 3 minus 1, 2? Where do you see that? So S minus 3 wait, minus 3 minus 1, 2? Oh, I see. I see. So this should have been I dropped a minus sign. Okay. So then it should be a plus here, right? I think so. Anyway, I think we're about out of time, but so let's go over this. I'll come back with a solution first thing next time. I dropped a minus sign, but I don't want to waste your time redoing these calculations right now. So I'll redo them in the privacy of my own home, and then I'll show you what I got next time. Yeah, so I think I made a calculational error here. Plus 5s. Yeah, let me get back to you about that. I think I made a couple mistakes, but let me just emphasize that although I made some computational errors, this is the correct way to do it. Like set the two lines equal to each other and then find S and T such that they intersect. Okay. Oh, the angle at which the vectors intersect? Is that? Oh, so for the angle that they intersect, I would probably use, let's see, probably you'd use the dot product, right? So you can use the dot product, and then I think you get something like S dot T is equal to, if S, sorry, not S and T, like V dot W is equal to V W cosine theta or something, right? And so you can take the dot product like this and then solve for cosine theta. Oh, so if you try and use the dot product on vectors that don't intersect, that's a good question. What you're going to get is, so if you have two vectors that don't intersect and you try doing this dot product trick, what it's giving you is, it's as though you move the vectors until they intersect and then find the dot product, okay? So you should do this. All right, so sorry about the mistake at the end, and I'll get back to you on that. All right, so see you next time, and feel free to stick around if you have questions.